Welcome to today's paper reading. Today's paper is titled, Strategic Chain of Thought, Guiding Accurate Reasoning in LLMs Through Strategy Elicitation. This paper was published on the AR14 preprint by Wang and colleagues from Huawei Technologies Limited and various universities. The Strategic Chain of Thought (SCoT) methodology is designed to improve the reasoning capabilities of large language models, LLMs. SCoT employs a two-stage approach within a single prompt, first eliciting an effective problem-solving strategy, and then using it to guide the generation of high-quality reasoning paths and final answers. This method aims to address the instability often seen in traditional chain-of-thought methods. Experimental results show significant improvements, with a 21.05% increase on the GSM-8K dataset and 24.13% on the tracking objects dataset, both using the Llama 3-8B model. Additionally, the SCoT framework has been extended to include a few-shot method with automatically matched demonstrations, yielding even stronger results. These findings highlight the potential of SCoT to substantially enhance LLM performance in complex reasoning tasks. The rapid development of large language models, LLMs, has demonstrated their effectiveness in reasoning tasks, particularly through the chain of thought (CoT) paradigm. CoT has become a fundamental component in natural language processing due to its ability to enhance reasoning capabilities. However, the CoT approach faces challenges in complex reasoning tasks, primarily due to variability in the quality of reasoning paths. To address these challenges, the authors propose a novel approach called Strategic Chain of Thought (SCoT). SCoT improves the quality of CoT path generation by incorporating strategic knowledge through a two-step process. Experimental results show substantial improvements, with a 21.05% increase in accuracy on the GSM-8K dataset and a 24.13% increase on the tracking objects dataset, validating the effectiveness of the SCoT approach across multiple domains. Figure 1 compares the Strategic Chain of Thought (SCoT) method with some popular approaches in the field. SCoT stands out as an efficient single-query method that does not require external knowledge sources, unlike other methods that may involve multiple queries or rely on additional knowledge integration. This distinction highlights SCoT's efficiency and practicality in complex reasoning tasks. The method section introduces strategic knowledge, which refers to well-defined methods that guide reasoning towards correct and stable solutions. This knowledge enhances the stability of chain of thought (CoT) generation. Building on this, the Strategic Chain of Thought (SCoT) method is proposed, which involves eliciting strategic knowledge before generating an answer. This method includes steps to identify and apply strategic knowledge. Furthermore, the few-shot SCoT approach refines the SCoT method by leveraging strategic knowledge to select demonstrations. This involves constructing a strategy-based demonstration corpus and incorporating few-shot examples to guide the model's final prediction. Figure 2 illustrates the zero-shot and few-shot Strategic Chain of Thought (SCoT) frameworks. The zero-shot SCoT framework is represented by the solid line in the middle, while the few-shot SCoT, which incorporates selected demonstrations, is represented by the dashed line on the right. The few-shot SCoT builds upon the zero-shot SCoT by integrating strategic knowledge-based demonstration corpus. The construction of the demonstration corpus involves generating SCoT answers and comparing them with ground truth to validate and compile accurate question SCoT answer pairs. This figure highlights the progression from zero-shot to few-shot SCoT, emphasizing the role of strategic knowledge in enhancing the reasoning process. Figure 3 presents the prompt templates designed for both zero-shot and few-shot Strategic Chain of Thought (SCoT) methods. These templates are composed of 5 key components: role, workflow, rule, initialization, and task input. The workflow component integrates a 3-step process aimed at identifying and applying strategic knowledge to solve problems. The first 2 steps focus on eliciting strategic knowledge, while the third step applies this knowledge to generate the final answer. This structured approach enhances the reasoning quality of large language models by ensuring a systematic and strategic problem-solving process. Figure 4 demonstrates a workflow in a math task prompt, specifically showing how to use the arithmetic sequence sum formula to solve a problem. The task involves summing all integers in the range from -25 to 23. The workflow includes identifying the relevant mathematical formula, applying it to the given range of integers, and calculating the sum using the formula S equals number underscore of underscore terms slash 2 asterisk, first underscore term plus last underscore term. This example illustrates the strategic application of mathematical knowledge to solve a specific problem. The experimental setup for validating the SCoT method includes a variety of datasets and tasks. For mathematical and physical reasoning, datasets such as MathQA, Aqua, GSM-8K, and Arc Challenge are used. Common sense and multi-hop reasoning tasks are evaluated using Common Sense QA and Strategy QA. Spatial reasoning is tested with the tracking object dataset. The models utilized for this validation include the Llama 3 series, Llama 2 series, Mistral 7B, Qwen 2 series, and ChatGLM 4-9B. Baselines for comparison include zero-shot prompts, self-consistency, and step back. The performance metric is accuracy, calculated as the average of 3 independent inferences. The strategic chain of thought SCoT approach has been empirically evaluated across various datasets and models. In zero-shot settings, SCoT significantly outperforms the chain of thought CoT approach, particularly on the GSM-8K dataset where accuracy increased from 52.11% to 73.16% after incorporating strategic knowledge. Additionally, SCoT achieved a 24.13% improvement on the tracking object dataset. The Llama 3-8B model showed an average improvement of 6.92% across all datasets, while the Mistral 7B model demonstrated an average improvement of 3.81%. SCoT also performed better than step-back and self-consistency methods in most cases. Furthermore, the SCoT framework was extended to support few-shot settings by automatically matching demonstrations, resulting in even stronger performance. The SCoT one-shot minus, which uses strategy match demonstrations, showed significant performance improvements across most datasets, highlighting the effectiveness of the match demonstrations. The SCoT one-shot, combining both strategic knowledge and strategy match demonstrations, achieved the best results overall. Figure 5 illustrates the accuracy percentages across 3 datasets for different scales of Llama 2 models. The data shows that SCoT enhances accuracy across all model sizes, with a noticeable trend of diminishing performance improvements as model size increases. Additionally, larger models are observed to produce chain of thought paths that include strategic knowledge in zero-shot settings. Table 1 presents the accuracy percentages of Llama 2-8B and Mistral 7B models across various datasets. The SCoT one-shot minus method, which uses demonstrations matched by strategy, shows significant accuracy improvements. Notably, SCoT one-shot minus outperforms other methods in most datasets, highlighting the effectiveness of strategic knowledge integration. Table 2 presents the accuracy percentages of 7 models across 3 datasets, MLU, SQA, and tracking object. Notably, the SCoT zero-shot method maintains 100% accuracy on the tracking object dataset, while the Llama 3.1-8B model experiences a slight decrease in accuracy when using SCoT on the MLU task. Across the datasets, accuracy improvements for other models range from 1.11% to 24.13%, highlighting the effectiveness of the SCoT method in enhancing performance. Table 3 presents the results of an ablation study on the components of the SCoT prompt. The study evaluates the performance of the Mistral 7B model with various prompt configurations, including the addition of roles, workflows, and markdown formatting. The table also includes results for SCoT in zero-shot, one-shot, and three-shot settings, highlighting the impact of these components on model accuracy. Table 4 presents a comparison of the token lengths generated by the SCoT and CoT zero-shot methods across different datasets. Notably, the Mistral 7B model shows a decrease in token length on the GSM-8K dataset when using the SCoT method, which is attributed to the model's tendency to repeat answer spans in CoT zero-shot. The SCoT method averages a token length 1.5 times that of CoT, indicating a manageable efficiency trade-off. Figure 6 illustrates the differences in paths generated by chain of thought, SCoT, and strategy-based chain of thought, SCoT, across various domains. In mathematics, SCoT tends to solve problems using inequalities, potentially leading to miscalculations, whereas SCoT ensures accuracy by considering all constraints. In physics, SCoT successfully elicits the correct formula, avoiding misguidance by specific phrases. For multi-hop reasoning tasks, SCoT focuses on the overall context, generating more complete logical reasoning compared to SCoT's detail-oriented approach. The authors conducted a preliminary test to demonstrate that the experimental results are not influenced by human-crafted prompts but rather due to the concept of SCoT. They used Qwen 2-72b to automatically generate prompt templates based on the SCoT concept and tested these on the Aqua dataset. The results, presented in Table 5, show that while the accuracy of automatically generated SCoT prompts is lower than that of manually crafted SCoT prompts, it is still superior to zero-shot SCoT performance. Specifically, the accuracy of automatically generated SCoT prompts is 31.89%, compared to 33.6% for SCoT zero-shot and 29.13% for SCoT zero-shot. This suggests that the automatic generation of SCoT-based prompt templates is feasible. Table 5 presents the accuracy percentages of different methods using automatically generated prompts based on the SCoT concept. The results show that the manually crafted SCoT prompts achieve the highest accuracy at 33.6%, followed by the automatically generated SCoT prompts at 31.89%. The baseline SCoT zero-shot method has the lowest accuracy at 29.13%. This indicates that while automatic generation of SCoT prompts is feasible, it does not outperform manually crafted prompts but still surpasses the baseline SCoT method. In this paper, the authors introduced the strategic chain of thought SCoT, a method that enables large language models, LLMs, to autonomously generate an optimal chain of thought path. By integrating a structured workflow for eliciting and applying strategic knowledge, SCoT enhances the model's ability to produce high-quality outputs. The authors further extend SCoT to a few-shot version by matching demonstrations through strategic knowledge from a predefined strategic knowledge-based corpus. Experimental results demonstrate the effectiveness of both zero-shot SCoT and few-shot SCoT. Overall, SCoT offers a promising framework for improving the quality of reasoning paths in LLMs. Future research will focus on evaluating its effectiveness with more complex problems and exploring further applications. Thank you for watching.